academic environment. And I'm liking what I'm seeing. But there are other aspects. I mean, I'm the director of graduate studies at Columbia, and I like this job.
We should chat, because I just started at this.
You just started at I'm not sure I have
We can commiserate.
You don't like the job.
It's a very interesting and challenging one. It's a growth opportunity.
So then everything is happening here. They will be rearranging the room for the ITC
So yeah, they rearrange everything.
My days, the ITC colloquium used to be in the other building, downstairs, I think, right?
Yeah.
Pratt, that's right, that's
And
right.
then we would come here for lunch.
For lunch, yeah.
So last time they were fixing something here, and we had the ITC luncheons at Pratt, and that was too crowded,
Yeah.
right?
Yeah. It doesn't work.
People were sitting outside, it was like,
Yeah.
couldn't see anything.
I can imagine, yeah.
We were sitting on the floor at some point.
Yeah, we were sitting.
All right.
Maybe we can start. Yeah. Okay. So welcome everyone. It is a pleasure to host Lorenzo Sironi. He's visiting us from New York City. So Lorenzo earned his PhD from Princeton University in 2011. And then he was a NASA Einstein Fellow and an ITC Fellow here at TFA. So some of you might know him already.
Many familiar faces. I see.
Very familiar face. And afterwards, he moved to, he joined Columbia University, where he holds the position of assistant professor. And today he will be talking about reconnection-powered emission in black hole jets and coronae. So,
All right.
Floor is yours.
Perfect. Okay. It's a great pleasure to be back here. As I was telling many people this morning, many good memories in this building and around this building, mixed feelings coming back. Weird feelings as well of seeing what has changed, what has not changed. But I'm happy to see many familiar faces that I truly enjoyed interacting with when I was here, and hopefully in the next couple of days, lots of more scientific interactions, discussions coming along as well. So I would like to present work that we have been doing in the last few years towards understanding this mysterious phenomenon, reconnection. I will be defining what it is, and its role in explaining maybe some of the most puzzling mysteries of emission in astrophysics, especially as it concerns the environments nearby black holes jets, black hole coronae. What is reconnection? And I'm using here the words of Russell Kalsrud, maybe one of the pioneers of the field of plasma astrophysics, the physics of plasmas applied to astronomy. At its 90th birthday party, Enrico Fermi told me to study reconnection 70 years ago. Here we are, we still don't understand it. Now, this may be true, may not be true. Wikipedia seems to know what reconnection is. This is a movie from that beautiful source of information. Reconnection is a process by which you're taking field lines going in one direction, blue, field lines going in the opposite direction, red. They meet in this midplane region of intense electric current, and they change their large-scale macroscopic geometry, topology. They do that, though, by microscopic small-scale effects that are happening exactly in this region. So they end up half blue and half red advected out in the left and right direction. In this process, the magnetic energy, some of the magnetic energy can be released to the gas, to the plasma, and potentially produce explosive phenomena. So reconnection is actually not something that is peculiar to high-energy astrophysical systems, even though this is the subject of my presentation. It's actually happening all the time very close to us. This is an event of a restructuring of these magnetic loops near the solar corona, which then gives rise to this coronal mass ejection, which can affect space weather in a dramatic way. Even closer to Earth, this is a sketch, this is not now an image, the solar wind is impinging onto the dipolar field of the Earth, triggering reconnection here. These snapped field lines move back, and you have another reconnection episode on the night side as compared to where to the day side reconnection that is happening ahead of the Earth towards the sun. So this event of rearranging the magnetic field geometry is happening very close to us. The peculiarity of the astrophysical systems, the high-energy astrophysical systems in particular, is encoded in this parameter, which I would really like to focus your attention on because it will come back over and over in my presentation. I'm going to call it magnetization. It's basically, apart from a factor of 2, the ratio of the magnetic energy density to the rest mass energy density of the plasma, of the particle. This means that if you are dissipating this energy, the energy goes to the particle, and if you are in the astrophysically peculiar regime of sigma, magnetization much larger than 1, then the available magnetic energy released to the gas can immediately make the gas become ultra-relativistic. So it's a good way to energize the gas, the plasma. And in fact, the main difference between near-Earth environments, whether that is lab experiments or near-Earth magnetosphere conditions, and the astrophysical systems that are of relevance for this presentation, is in this value of the magnetization. Much less than unity here, much larger than unity here. And we are calling these systems in high-energy astrophysics magnetically dominated or relativistic. And as I said before, this relativistic jargon, the word relativistic just stems from the fact that if you are releasing that magnetic energy into the gas, the plasma immediately becomes of typical relativistic temperatures, relativistic energies. Equivalently, this condition can be cast as the Alfvén velocity. This is the typical velocity of hydromagnetic waves in the plasma, close to the speed of light. These two statements are equivalent. So let me introduce a few sort of like words that describe the physics of reconnection. And I forgot to mention it at the beginning, questions are welcome at any time. Okay, so at the end, during the talk, if something is not clear, stop me. I think I want this to be as informative as possible. Avi.
What are the observational consequences of the reconnection in the Earth's magnetosphere? Do we see those pulses then? We see
actually high energy jets. They come, let me step back. Let's see, hopefully this movie will work again. So we see actually high energy particles eventually precipitating towards the poles of the magnetic poles of the it's one type of the aurorae. And they are attributing it indeed to this pulse of high energy particle released mostly from night side reconnection. So we don't have in situ evidence, but we have sort of where the reconnection happens, but we have indirect evidence of those high energy particles eventually being channeled to the magnetic poles of the Earth. So let's go back to our Wikipedia picture. We will be, from now on, in a regime in which the magnetization is much larger than unity, or equivalently, the Alfvén speed is over the speed of light. In addition to the oppositely directed fields that are depicted in this image, it's often common to define an out-of-plane or guide magnetic field, sticking in this case out of the page or into the page, it doesn't really matter, but it's uniform. The direction does not change across this interface. So its energy cannot really be used, even though the dynamics of reconnection can depend on whether it's there or it's not there. The peculiarity of the relativistic regime of reconnection is the fact that it goes fast. And fast, I mean that the rate, the velocity at which the plasma flows into this middle region can be as large as 0.1 of the alpha n velocity, but the alpha n velocity is the speed of light in this case. So you have plasma flowing in at speeds that are 10% of the speed of light. We cast it in a different but equivalent form by saying that the rate at which relativistic reconnection can dissipate the magnetic field is 0.1 of the speed of light. So there is a high rate at which the magnetic energy is being dissipated in a relativistic, magnetically dominated system as relevant for high energy astrophysical sources. Where does the energy go? Part of the dissipated magnetic energy just goes into moving the plasma away, left and right in this picture. This outflow velocity contains part of the dissipated magnetic energy. Some of the energy can also be released as heat, resulting in thermal particles or non-thermal particles. So I'm going to present here a sketch, and you'll see many realization of this sketch in the rest of my presentation with real data at that point, or simulate as much as simulation is real. This is a Maxwellian, a standard thermal distribution. At higher energies in log-log space, the straight line will be a power law distribution. This is typically called non-thermal part of your distribution. Non-thermal, power law, these are synonyms. Reconnection may heat the plasma, but it may also give a non-thermal distribution of particles. In order to accelerate particles to non-thermal energy, especially to non-thermal energies, you need electric fields. And there is a natural electric field of a reconnecting system. This is just the electric field associated with the fact that the plasma is flowing in. So it's related to the magnetic field by this ratio of the inflow velocity over the speed of light. As I said, the inflow velocity is 0.1 of the speed of light. So you can have electric fields in reconnection. An electric field is what you need in order to energize particles that can be as large as 10% of the magnetic field. It doesn't get any better than this. I mean, if you're interested in accelerating particles in the universe, the most that you can really hope for is a fraction, is an electric field that is a fair fraction, 10% of the magnetic field. And that's what reconnection naturally gives you. So it's a very good candidate for accelerating particles.
You get cross-speed drift because of that?
So this is exactly where this inflow motion is, right? So the electric field is actually sticking out of the page. The magnetic field is like this or like this. So this velocity is indeed the E cross B velocity. And similarly for the outflow, it's a different E cross B because the magnetic field is weaker. The electric field is the same. So it's a faster outflow. I'll get back to that. But effectively, the motions that you're seeing here are E cross B motions. So how are we approaching the understanding of whether reconnection can indeed be a source of non-thermal particles, and as a result of that, possibly a source of the non-thermal emission that we see in the universe? And the most fundamental method is a method that I really love is the particle in cell method. It's basically the same as particle mesh technique for collisionless gravity. You're relying on the Lorentz force and Maxwell's equations, so electromagnetism 101. You're following particles in a Lagrangian way, moving them according to the Lorentz force. Each particle is carrying a charge and a current. Since it's moving, you are depositing the current, combined current from all the particles onto a numerical grid. On the grid, you solve for Maxwell's equations. You get the electric and the magnetic fields. And then you use the electric and the magnetic fields back into the particle equation of motion to push the particles around with the Lorentz force. So this is how the system is coupled and non-linearly evolves. All great. You're capturing the right physics for these particles, individual particles. The bad thing is that the separation between the typical plasma scales that you need to resolve in astrophysical scales is often very large, / enormous. For the application that we'll be discussing at the ITC luncheon is enormous. Just to give you some numbers, the typical length scale is called plasma skin depth. It's 10 to the 5 centimeters for a density of 1 particle per cc, vanilla ISM densities. The typical time scale is the inverse plasma frequency of order 10 to the minus 5 seconds. So you can think now about how different this is from astrophysical scales. What this implies is that we need massive simulations, number one. And number two, we need very careful, physically grounded extrapolation from the results of the simulations up to astrophysical scales in order to say anything that is informative and sensible. So how does reconnection look like in a PIC simulation? Let me just give you an idea of a sort of like standard vanilla 3-dimensional PIC simulation with a magnetization of 10. So this is 10 times more energy in the magnetic field than in the rest mass of the particle. And we're showing the density here. The magnetic field flips along this direction across the interface that will be shown that as isocontours of the density. So we're trigger in the middle. The beginning is a consequence of our initialization. You see these two fronts moving out, outflow boundaries. All of these structures are self-consistently produced by the plasma physics of reconnection. We call this density structure plasmoids or flux ropes or magnetic islands. I will be using these terms interchangeably. It's just conglomeration, it's just over-densities that are produced as part of the evolution of a reconnecting system. And you see that they evolve in a hierarchical way. They start from small scales, then they can merge with each other, they grow to bigger scales, and bigger until they eventually exit from the outflow boundaries. So it's a very dynamic system. But what I'm giving you so far is a fluid picture. This is a density. You could get the same without following individual particles, which is really the power that a particle in cell simulation gives you. So the question that, as I said, the particle in cell method can help to address is, okay, what about the particle distribution? What is the particle distribution coming out of a reconnecting system? So this is how I'm going to spend the next few slides. Yes, Magda.
So maybe you're getting to this, but you're actually simulating a finite number of particles, right?
Yes.
Why do you need cells?
Good question. So you are following the particles in a Lagrangian way always. The cells are used to solve for Maxwell's equations. So you're discretizing your Maxwell's equations on a grid, and the particles are then putting their information onto the grid via their current. So you need a source term for Maxwell's equations, which is the current. You're gathering the current from the particles and depositing on the grid. There are other strategies. I mean, one could do just forces that are uncorrelated, binary forces between the individual particles, and that will be solving the same set of equations. The grid will automatically give you a framework for solving Maxwell's equations in an easier way, conserving all of the right properties. Div B is 0. The electric field is staggered with respect to the magnetic field. So it gives you the conservation properties in a more natural way.
So just following up, so does that mean that your resolution or accuracy is set by the size of the cells rather than the number of particles?
So the number of particles is determining the statistics. So there is a particle noise argument. If you have too few particles, you're not able to construct the current, which is basically the first moment of your distribution, in an accurate way. Think about having just one particle in one cell. You have no information about really the current, which is like an integral over the distribution function of the particle. So having more particles helps to reconstruct the current better. But in terms of setting the spatial resolution of your simulation, this is where the cell enters. Now, the question of resolution is different than maybe what you have in mind for MHD, because there is always a scale here that you need to resolve, and it depends how well you resolve it, but this is giving you the minimal requirement for how big a cell can be. It cannot be any bigger than your plasma scales, otherwise the method just fails. It's not stable anymore. Yes?
As a follow-up, so what's the typical resolution for particles?
How many particles? So let me cast it in terms of just how many particles, and then particles per cell. So typically we have of order 10 particles per cell. For some other problems, it can get up to 100 to 1,000, but the average is about 10 particles per cell. This is enough to construct their first moment in a reasonably accurate way. In terms of the overall number of particles in the simulations, I would say of order like the biggest can be of order 1 trillion particles.
And a cell is what, plasma?
And the cell needs to be a sub-plasma scale. So the plasma scale is typically resolved with a few cells to 10 cells.
So how many electrons or protons are expected on this? How many electrons or protons per particle?
Well, that's a very good question. We'll come back to that. So this is maybe getting too technical, but the point is that what I'm selling as individual particles, these are really not individual electrons. The charge of the particles is the charge of a macroparticle, and how the idea is that all of these electrons will be conglomerated into a macroparticle, which is moving around coherently, conserving the charge to mass ratio, because all of them have the same charge, all of them have the same mass. But in reality, the charge is much bigger than it should be. So depending on the problem, this can be many or many. But for a precise number, we need to think about a specific problem. All right, so what can reconnection do for us? As I said, the beauty of this method is that it can capture the non-thermal properties of particles, non-thermal distributions of particles, and I would like to focus the next few slides on that. What do we understand about the physics of particle acceleration in reconnection? So the first part of my talk is going to be more physics-based on just the mechanics of how reconnection works, and then the second part will be, as I said, probing the multi-wavelength signatures of reconnection in high-energy astro sources. And I'll be listing the people that I'm doing the work with, so you might recognize some faces, especially later on. Let me give you the punchline first. Reconnection naturally makes broken power laws. You should think about this plot as a log block plot. This is the Lorentz factor or the particle energy, and this is how many particles you have with that energy. So the question of phrasing the particle distribution is a question of how many particles you have with a given energy. At low energies, this slope, this P is the slope, can be -1 or steeper. So the hardest it can get is the n d gamma proportional to gamma to the -1. This phase I call injection. Higher energies, we find that the slope is nearly universal, meaning independent of the magnetization parameter that I defined before, and the slope is -2. So the n d gamma goes like gamma to the -2. And I'll be describing these two phases separately, but let me comment on the break first. So the break is happening at a few times that magnetization parameter. So that's quantifying the ratio of the magnetic energy per unit rest mass. It's not surprising that the break is happening there, but it's an interesting break. Is the phase here of any interest? Injection we typically call the phase of early acceleration, so the initial stages of acceleration. So for electrons, the right way to cast this magnetization is the magnetic energy density in units of the rest mass energy density of electrons. So this injection stage brings already the electrons up to quite relativistic energies. So it's not to be neglected. The early stages of acceleration can already give a good jump in the electron energies, making them already participating in some reasonable emission signatures. Typical radio emission requires 10 to the 4, 10 to the 3 in Lorentz factor electrons. So you naturally get that from the injection stage already. So let me focus on the injection part. What's controlling the physics there? So you all know from ideal MHD that the electric field is always written as minus V over C cross B, where V is the fluid velocity. Now the most interesting physics in the injection stage of reconnection is happening exactly where MHD fails. So the particles get this injection stage. If they interact with fields that cannot be written as ideal MHD, we call them non-ideal. Electric field cannot be written as minus V over C cross B. So the regions that MHD is neglecting are the most interesting one for these early stages of acceleration. And this can be declined in two different ways. For low guide fields, and let me remind you, the guide field is the component sticking out of the page that does not enjoy or suffer dissipation. This can be cast as electric field larger than the magnetic field. If you have an electric field locally larger than the magnetic field, clearly it cannot be written this way. Alternatively, for stronger guide field, you can have a parallel electric field parallel to the magnetic field. And again, this is not a configuration that you can write with this cross product. Okay? There is no component of the electric field parallel to the magnetic field in ideal MHD. So these two are criteria that clearly are broken in ideal MHD, and yet this is the electric field that is doing most of the work for the injection stage. Let me justify this better. This is a vanilla simulation of reconnection. It's even 2D, because a lot of this injection physics does not need 3 dimensions. And you'll see a bunch of particles here, the small dots, yellow, that are moving towards this mid-plane where the alternating magnetic field will meet. 3 particles are highlighted, orange, red, and yellow. Let's look at the red particle first. The bottom panel is showing its energy trajectory, so the energy as a function of time. And there is one specific time that is particularly interesting. It's happening now. There is an underlying dashed red line here, vertical, this indicates the position where the particle interacted with an electric field larger than the magnetic field. What's the consequence? The particle energy shoots up. There is no magnetic field prohibiting acceleration. The particle is just seeing an electric field. It's accelerated like crazy. Same thing is happening for the orange particle later on at the correspondence of its own orange dashed vertical line about now. This is an event in which the orange particle experienced an electric field larger than the magnetic field. Once again, it shoots up in energy. The yellow particle instead never had any vertical dashed line, never interacted with an electric field larger than the magnetic field, and its energy stays transrelativistic. The Lorentz factor is of order unity throughout. So this is a proof that the early stages of acceleration need effects that cannot be captured in ideal MHD. What's the second stage? Now this is different in 2D and 3D, so it requires 3D simulations. And I'm showing here slices across a 3D simulation. This is the direction of the alternating field. This is the direction across the midplane of the layer, and the z direction instead is the direction perpendicular to both in this picture. From the point of view of the alternating fields, this will be in and out of the page, as depicted here. And the same particle is plotted on both. So you'll see the trajectory of this particle. So the particle is stuck for a while in what we called before magnetic island, plasmoid, flux rope. But then it breaks free. And if you look at the z trajectory, it starts swimming, like freestyle, up and down the reconnection layer. This is a natural, actually, expectation of the way the magnetic fields are arranged. It's doing half of a gyration on one side, half of the gyration on the opposite side. The magnetic field is it's changing direction. The most important thing is that the way the particle moves is exactly aligned with the direction of the electric field. So the particle is in the best possible trajectory to experience all of the accelerating power of the electric field, which means very fast acceleration, as fast as you can get. So the energy gain rate, the energy acceleration rate, approaches, as I said, the maximum that you can think of. This is electric charge, electric field, speed of light. The particle will be moving at the speed of light. And the electric field in reconnection, as I said already, is 0.1 of the magnetic field. So this is really as fast of an accelerator as you can get. You are accelerating by moving along the electric field, with the electric field being a few tenths of percent or tenths of percent of the magnetic field. I'm going to close here the physics part. Given how fast this acceleration goes, you have very good prospects for accelerating ultra-high-energy cosmic rays in jets of active galactic nuclei and potentially gamma-ray burst jets. But I'll go to the leptonic part of my talk and the leptonic emission part of my talk afterwards. There were a couple of questions, Avi and then Ido.
So is it a coincidence that you have equal amount of energy per logarithmic energy interval, which is exactly what you get in strong shocks? So strong shocks perhaps have the same physics.
So it's a coincidence. I think it's a constraint. You cannot get any harder than this, right? Because otherwise you will be running out of energy. If you were to have a slope that is harder than -2, then all of your energy will be at the high energy end, and you're just out of the energy balance that your system can give you. So I think in both cases, this is an argument for why it cannot be harder than this. It could be steeper than this. The trajectories, I think, are very different. The shock physics is intrinsically, the shock physics is intrinsically diffusive. So you need turbulence that is keeping the particles in the system for long enough to be accelerated. Here, the motion is rather regular in the sense of like this just knows about the large-scale magnetic field, and in fact, the large-scale magnetic field is flipping its direction across this interface. Now, I'm saying this, but I'm also negating this at some level. Like if this structure that is present here is helping deflect the particles away so that they can continue in this swimming style motion. So there is a diffusive component in here as well. And most fundamentally, you can describe this acceleration process basically as a first order Fermi acceleration process due to the fact that these two regions are converging towards each other. So there are actually substantial similarities in the underlying physics. whether it's obvious that they give the -2, I think there are other constraints that relate to that. Ido.
I was going to ask, and maybe you're going to come back to this so we can talk about it later, but you said it's nearly universal to get this -2, but observationally when we look at these different systems that are, have these non-thermal particles, we find quite a broad range. So what else could...
Let me just be more specific. So the universal that I mean maybe is an oversell, but it's a statement of the fact that if you have a magnetization that is larger than a few, then it's no longer dependent on magnetization. That's really what I can say. If you have a non-relativistic system in which the magnetization is much less than unity, reconnection will give slopes that are actually highly dependent on the value of the magnetization. So it's a unique feature of the relativistic going to ultra-relativistic systems. And it's a unique feature of reconnection, and possibly shocks as well. Maybe all of this, maybe there is actually a common underlying reasoning that all of the accelerators, as long as they're relativistic enough, how relativistic they are does not matter. But yeah, the confinement of my statement was just related to reconnection, related to the high sigma regime.
Yeah, but even in those cases, when we look at gamma ray bursts, which are presumably all in the relativistic regime, we find ranges of this power law index between 2 and maybe close to 3.
3, yeah. I'd be happy to talk about that, because I mean, we have, not here, but we have seen very interesting dynamics in acceleration at relativistic shocks that are relevant for GRB afterglows, such that the portion that is actually -2 is of a rather limited energy range. And you can have then a bridge towards your Maxwellian, very extended, that if you are fitting it just with one power law, may be closer to a -3 slope. So I think there is some interesting dynamic just related to the shock physics and the way the shock physics works for that part. There are a question in the back. And if you don't mind, let me check the time just in case.
The first part of the acceleration process that you call injection, so does it efficiently accelerate the majority of particles participate like in the plasma or like a small fraction of those?
It's a great question. So I had a number here which I did not emphasize. So this is the fraction of particles out of the yellow ones that encounter the region with E larger than B. And it's over 20%. So you can call that injection. About 20% of the particles go through what I would call injection physics. Yes?
Just to follow up to Avi's question, what says the upper limit for
the energy? Great question. So then it depends, really. I mean, if you're electrons and they cool, then there is a cooling limit. I'll be talking about some cooling cases later on. If you have ions and they don't cool, which is in itself an assumption, I mean, there are interesting sources in which the ions do cool and make neutrinos, then it's what's called the Hillas limit. This is a limit in which the gyro radius of the particle is bigger, or it's comparable to the size of your system. And then the particle can just not sample anymore let's say, the convergence of the flows that ultimately gives rise to the energization.
So the most relevant size of the system here is like the size of the partnership?
So then let's talk about the application, because then it has to be specific towards the global picture of what we really care about. All right, so this is a sketch I got from Charles Gamy on how complicated the environment of a black hole can be. There are all these energy transport processes, which Ramesh understands, but I'm not really familiar with all of them. So I asked my daughter to put some colors on it. This is what she came up. And I think this is a good way of looking at this picture with a little bit of blurry eyes. So you have your accretion flow here, but she didn't do it, but it was a nice joke. This is the accretion flow. This is the accretion flow. This is the wind that may be emanating from the accretion flow. There is a jet powered by the spin of the black hole. If there is a jet, a boundary between the jet and the wind. And then you have this current sheet, which has been unveiled by recent general relativistic MHD simulations as being present, at least in the state in which the black hole is accreting material with significant magnetic flux. So one episode of reconnection, one instance of reconnection, as I said, is in this magnetospheric or equatorial current sheet. These are general relativistic resistive MHD simulations performed by Bart Ripperda. And as I said, the current sheet appears in the so-called magnetically arrested state, in which you're feeding into the black hole enough magnetic flux such that the black hole can no longer get any more flux. And then the flux gets dissipated through this equatorial current sheet, and the black hole can continue accreting in episodes that are accreting versus erupting episodes, repeating. I'm not going to discuss the observational implications of this, but this current sheet is there. Rather, what I'm going to give an emphasis on is the boundary of the relativistic jet. This is larger scale now. And you see that it lights up in temperature, so that means that some dissipation is happening there. And I would argue that reconnection plays an important role for the dissipation of the jet boundary. And then I'll say something about the corona. I'm not going to point where the corona is. I'm going to give you at the end maybe a hint of one possibility for what a corona might be, but let's wait for that. So jet wind boundary, and you'll see some familiar faces here. So the motivation here is to understand why the boundaries of relativistic jets are brighter than their core. This is beautifully illustrated here in the M87 case. This is not the only case. I think every jet that we see in the radio close enough to the black hole that it's powering it is seeing these edges being brighter than the core. So some dissipation needs to be happening there. And there is an obvious candidate. The jet is moving faster than its surroundings. So you have a velocity shear between the jet and the surrounding material. Whenever you have that, you have a candidate instability. Kelvin-Helmholtz in its realization with clouds in our atmosphere here, but you can sort of like imagine the same thing happening at the boundaries of relativistic jets. Is this real? Yes. Recent general relativistic MHD simulations are indeed showing the presence of these waves curling up as typical Kelvin-Helmholtz vortices. So that picture of waves, the picture of vortices in our atmosphere has an obvious equivalent at the boundary of our best representation of what a relativistic jet from a black hole is. But a key question that we have yet to address and that MHD cannot address is what is the nonlinear outcome of the Kelvin-Helmholtz or these Kelvin-Helmholtz rolls at the jet boundary? What can give in terms of accelerated particles and emission? So we oversimplify the problem and we put it in a particle in cell box. The jet is this yellow region. It's electron-positron plasma. It's moving relativistically up. It's threaded with strong magnetic field. There is a poloidal component of the field, which is depicted here, and a toroidal, for the jet point of view, sticking out of the page. The outside is a regular electron-ion plasma, weakly magnetized, so what you would expect for the wind. So we're really looking at the interface here between a magnetically dominated electron-positron jet and a weakly magnetized electron-proton wind. What happens? Let's see what happens. So the first thing that you will see is that typical Kelvin-Helmholtz rolls actually do happen. So this system is unstable to the Kelvin-Helmholtz instability. And we've actually worked out the MHD linear dispersion analysis for these modes, compare them with the peak simulation, which is a kinetic, so non-MHD description, and they match beautifully, which means that the peak simulation is on scales that are large enough to capture MHD fluid type dynamics. And the system is very rich. It produces these vortices break, you produce small scale structure. What I would like to emphasize, and this is the right time for emphasizing it, is that reconnection is part of this story. You started initially with field lines. These are field lines, not flow lines, pointing up. But then as a result of the nonlinear stage of Kelvin-Helmholtz, they wrap up onto themselves. So now they're pointing down. And if they smash together, which they do, then you have a natural outcome, a natural product of reconnection here. In the late stages of evolution, this partially as a result of reconnection, you have this region at the boundary that started magnetically dominated with large magnetic fields and ends up with roughly equipartition between the gas pressure and the magnetic pressure. So what we call a plasma beta of order 1. Particles are accelerated as a result of this interaction, self-interaction on the outskirts. This is a particle spectrum, so it's computing how many particles you have as a function of their energy. The movie will run again. So what you can see is that when the nonlinear stage of the Kelvin-Helmholtz happens, the spectrum shifts rather abruptly to higher energies as a result of reconnection dissipated energy byproduct of the nonlinear stages of the Kelvin-Helmholtz instability. So Kelvin-Helmholtz gives reconnection, which gives high energy particles. And I'll emphasize 3 implications. As I said, the primary motivation was the limb-brightening of relativistic jets, so the fact that they're brighter on their outskirts. This dissipation channel offers a natural explanation for that. The second aspect is the peculiar structure of the jet post-dissipation. The core is basically untouched. It's still moving relativistically. We call it spine in models of blazars, of jets from active galactic nuclei pointing at us, surrounded by a sheath that has a plasma beta over a unity, and it's moving at transrelativistic velocities, so slower. And these models have been employed to model the blazar emission without actually knowing where these two structures could come from, and the nonlinear stages of Kelvin-Helmholtz provide an obvious realization for that. And finally, and this is work done by Jordi, we are actually able potentially to see these Kelvin-Helmholtz type waves / vortices in action. So these are GRMHD simulations that are ray traced with polarization accounted for. And the outcome is that if you are having all of these structures that are messing up your jet boundaries, you naturally are led to lower polarization degrees as compared to a laminar jet. So there is some hope that the polarization signal potentially for the next generation EHD will be able to assess whether the jet boundaries are indeed as active as we are envisioning here and as recent GRMHD simulation seems to suggest. I'll close up on the jet boundary story, and now apparently unrelated black hole X-ray coronae story, and then we'll try to unify the two at the end. Let's see how much I'm doing. So the motivation here is the hard state of X-ray binaries. A black hole fed by a star. They seem to exist in 2 different stages, the so-called soft state. It's thermal emission around a keV from the accretion disk. This is standard, if you want, Shakura-Sunyaev disk. On the other hand, the hard state peaks at 100 keV, and it's interpreted as upscattering of keV photons, of disk photons, by some hot electrons in this unspecified corona. Corona is kind of like unicorn, right? So everyone, or at least every kid, is very convinced that it exists, but yet the properties are unspecified. So I will try to unveil this unicorn a little bit. So the standard model is the following. You have a cloud of hot electrons sitting somewhere. The electrons have a temperature of 100 keV. The disk photons come into this cloud of hot electrons. The hot electrons are upscattering the photons, moderate optical depth. You can build a spectrum that matches the observation. Does it work? Not really, because none of the energization process that we can think of is capable of keeping the electrons at such high temperatures despite the tremendous cooling losses. The systems are filled with photons. The cooling time is much smaller than the dynamical time, which is the typical time to resupply your available energy. And this just means that you cannot envision any reasonable heating process that would keep the electrons as hot as 100 keV. So are we done? Are we just failing in the explanation of the corona? Not really, because internal motions / temperature are not the only source of motions. This would be hot but steady. This is cold but moving. So you have bulk motions that can also upscatter if the bulk motions are with respect to the isotropic photon field. So you can have photon coming in, upscattered by the bulk motions of otherwise cold electrons, and comptonize potentially to X-ray energies. What is the source of the bulk motions? By now you can guess my answer. Reconnection is a very good source of that. So this is now radiative peak simulations in which we are accounting for cooling losses. The parameter that accounts for the cooling losses, that incorporates the cooling losses, is this gamma critical that is obtained by equating how much power you can get from accelerating particles in reconnection to how much power you're going to lose because your Compton losses. So it's a parameterization, if you want, of this photon energy density. Larger gamma critical means smaller URAD, means no cooling. Smaller gamma critical, larger photon energy density, more cooling. So I promised you bulk motions. And you can naturally see where the bulk motions are from, right? You have these overdense structures, the magnetic islands, the plasmoids that we started from. They're naturally moving within a reconnection scenario. They're actually snapped by the magnetic field that is advected out, that this is ultimately the source of these motions. And we can ask the question of how much the bulk motions contribute to the Comptonized signal. So the next two panels will address that. The first panel is showing the Compton emissivity, accounting for all degrees of freedom of the particle motion, so including the temperature, the internal motions, and the bulk motions. The last panel is the contribution, assuming that the particles move just dependent on their bulk motions. And what you see is that they're identical, which means that all of the Comptonization is happening not because the particles are hot. Actually, the particles here are non-relativistically cooled down, but because they move with some bulk motions, at right bulk motions, and as I'm going to quantify in a couple of slides. So reconnection naturally gives these bulk motions, and we're proposing this picture. You have soft X-rays coming from the disk. They're Compton upscattered, not because you have a cloud of hot electrons, but because you have relativistic or transrelativistic structures, density structures, that are moving as a result of the intrinsic dynamics of reconnection. And these motions, these bulk motions, can upscatter to 100 keV energies. So let's quantify this a little bit more. This is the particle spectrum, how many particles as a function of energy. You've seen this a few times already. In the strong cooling regime. The dark blue is the total particle spectrum, accounting for both internal motions and bulk motions. The cyan is accounting for bulk motions only. The peak is the same, which means that really you have reduced, as a result of cooling, your internal motions to non-relativistic values. They don't really contribute to where most of the particles are sitting. Even more interesting, you can try to fit it with a Maxwellian. You shouldn't, right? A Maxwellian is a statement about internal motions, about temperature. These are only bulk motions, at least for the cyan line. And yet, if you fit it with a Maxwellian, the Maxwellian turns out to have a temperature of over 100 keV. So effectively, your bulk motions in reconnection have an effective temperature that is exactly the temperature that standard Comptonization models are using to explain the signal, the X-ray emission that we see. We can go one step further and bring this to closure. We can trace photons through our time-evolving peak simulation and produce Comptonized X-ray spectra. The dashed line is for a magnetization of 3, so 3 times more energy in the magnetic field than in the rest mass of the particles. And it matches beautifully the data, which are the blue line here and the dashed line. So we only had to choose the magnetization, a few, and the optical depth of order 1, which is a standard assumption and common knowledge for coronal emission. And then the spectrum just comes out for free. John?
You need a large filling factor for the reconnection?
That's a great question. So ask me after the final few slides, and we'll talk about that, and maybe we won't stop talking about it. So let me conclude with the last few slides. What is the corona? Where is the corona? Maybe let's narrow down the scope a little bit. Where is a corona, or at least one option for the corona? I wouldn't be as bold as to say that there is just one explanation, but I'm going to present you at least with one potential explanation. So the insight here was given by general relativistic radiative simulations, general relativistic MHD radiative simulations with radiative transport to temperature. So as best that you can do. Matthew Liska was here a few years back. And they have shown that if the disk is threaded with enough magnetic flux, the outer disk is a standard thin disk. This is the left panel in these two figures. This is outer, larger distances from the black hole. Cold and dense. The inner disk transitions at a truncation radius, so there is a boundary radius between the outer disk and the inner disk, and the inner disk is hot and dilute and magnetically dominated in the same mad sense that I discussed before. It's a magnetically arrested state. So the innermost region really looks like a mad configuration, a configuration threaded and saturated with magnetic flux. So we just look at the inner region now. But we started with higher resolution. So this is the key movie for the next few slides. So I'm going to spend some time describing what you see here. This one is the ratio of gas pressure to magnetic pressure that I called beta before, the plasma beta. This is the magnetization, magnetic energy density over the rest mass energy density, which I discussed already a few times. And this is the flux threading the horizon as a function of time. So I'll let the movie run. The punchline is that you have reconnection structures all the time, or most of the time, at the jet boundary. So you see these blobs. Now I'll pause the movie, and probably I'll pause it at the wrong time. Oh no, that worked out fine. So you see these blobs at the jet boundary, natural byproduct of reconnection. Reconnection is happening all the time at the jet boundary, and it produces these structures that we clearly identify as reconnection plasmoids, magnetic islands, flux ropes. I'm going to let it go through the end. And then there is a panel that will appear here. This is our way of identifying what we should be calling jet boundary. And it's done with a cut in the plasma beta, the ratio of gas to magnetic pressure, and in magnetization. And the color in this boundary is the gamma square minus 1, which is really the amplification related to Comptonization. It's like how much you're Comptonizing per particle, if you want. So we'll come back to that. Okay? But this is just a way for us to select what we call boundary. And what I'm trying to convince you from this movie is that the boundary is very rich in reconnection episodes. This boundary is powerful. We can quantify it with the radial electromagnetic flux, the Poynting flux. You see that it's brighter at the boundary, even brighter than at in the core of the jet for very good reasons, that the toroidal field is stronger at the boundary. We can quantify how much more power the jet boundary is carrying as compared to the core, to the spine of the jet in this plot, which is a plot of time versus angle. So we're looking at the polar angle here for a fixed radius of 15 Rg. And this is the cumulative contribution. The blue is the boundary, and the green is the jet, which is sitting at 0 and pi. So we find that this boundary is actually carrying twice as much power as the inner core of the jet, and power comparable to m dot c squared. So really as much as you can get out of the system. So it's powerful, number one. And number two, it has the right energy scale. So let's come back to this plot of the gamma square minus 1, which quantifies the bulk motions in this region. These are purely bulk motions. I would not trust MHD in any respect for the properties of the particle distribution, but here we're just relying on bulk motions, and MHD should be perfectly fine with the bulk motions. So we can take the region that we are coloring here and compute the bulk energy spectrum. And the basic point that I'm reinforcing again is that regardless of distance, the different colors are for different distances from the black hole, you still can model the bulk energy spectrum as a effective Maxwellian with a temperature of order a few hundred keV, 100, 250 here keV. So this boundary has the right energy scale for doing the Comptonization that is needed for the 100 keV hard emission, hard X-ray emission. It's powerful. It has the right energy scale. So with that, I will conclude. Are we done? Have we found the corona? I would say if we found one corona, the unicorn is sitting there, maybe. We need at least two things to make this more compelling, and we're working on that. We need to trace photons through these global GRMHD simulations and produce Comptonized spectra. And we need to compare with IXPE results. They've challenged everything we thought we knew about the corona for the polarization degree that has been inconsistent with most models. We'll see whether this works out. Stay tuned. I don't have answers for this yet. And I'll be happy to come back to John's question related to the filling fraction. with that, I'm done. This is my summary, and I'll stop here. Thank you.
I think, is this working still?
So let me start by going.
5 minutes, yeah, for more questions.
Yeah, let me start by going back with the question of the filling fraction. I don't really have a good answer. That's why I postponed the question. But I think what I'm thinking about now is that for some cases in which we do not see an obvious KeV bump, let's say the case for Cygnus X1, then I would say my best interpretation is that the disk is truncated enough far out that the 1 keV flux from the disk is not very important, and the seed photons for the comptonization are produced locally by synchrotron. So at that point, you're just sort of like changing your perspective. It's not that you would expect a large keV flux going in all directions, and a fraction of it's intercepted, but you're producing them locally, so it's likely that a large fraction of it is actually going to be intercepted. AGN is very different in that respect, because you do see, even in states that are formally hard states, I'm not sure that's a good word anyway, but you do see a large keV contribution. And then the photons might come from the disk, and only a fraction of them be intercepted. But it's a great question, and I don't think I have all of the answers that I would like to have.
So speaking about AGN, all AGNs have X-rays, right?
Mm-hmm.
And only 10% have jets.
Yeah, great
So
question
this
too.
mechanism is not
Great question too. That's why I said a corona. I did not say the corona. I would be very curious to see how this strategy or how this identification of jet boundaries as an interesting region for comptonization changes when you have, let's say, zero spin, in which case you would not have a jet. These are nearly maximally spinning black holes. So you do have a jet, have a jet boundary, everything is good. I would expect, if you have a zero spin magnetically arrested disk, you'll still have plenty of reconnection episodes. I just don't know where they will be localized. Completely agree. I've also been struggling a lot with this question in the sense of like, what do we call a jet, right? Because a jet is a visible jet. There might be systems that have jets that are choked very near their source or disrupted by interactions with the surroundings, such that we're not really able to see them propagate to kiloparsec scales. So are we actually sure that there is no jet physics in such systems, or whatever we see as powerful jets is a statement of like, yeah, jetted sources are necessarily jets that we, this may be a little bit philosophical. Okay, but you got the point.
Yeah, so brief question about the scales of these vortices that do like the connection and acceleration. So as I understand, these vortices, they can appear like many parsecs from the jet core, from the jet origin, right? So does it mean that even in these scales and maybe even further away, there is still like pumping of the energy from the remaining energies in magnetic field to particle energy, so like acceleration we can go in?
It's a great question. I think the partial answer I can provide is that we now have the framework to check this explicitly. So if there were to be a simulation that can actually go beyond Bondi scales and give a good sense of the profile of the interface, we have the tool to say whether this is locally unstable. It's possible that the modes that you're exciting at the beginning are then transitioning to a state that is no longer unstable, right at like 40, 50, 100 RG from the black hole. But then the system is changing the surrounding at larger distances, and it may still be unstable at those larger distances.
But for, at least for M87 and for a few other jets that are seen with great resolution, we see these like instabilities or something very similar up to many parsecs away. So it's not hundreds of RG.
I agree. That's exactly my point. So whatever we are envisioning as the dynamics happening at 100 RG might saturate into a state that is quasi-stable for those distances, but then at larger distances it may no longer be stable, and then you have a way to pump the energy at those large distances. But I really wish we could have a description of the jet structure at those large distances that is motivated by the launching properties as well, and not just made up because it's an equilibrium that we can build. And at that point, we can run the dispersion analysis and see whether there are indeed occurrences of surface type instabilities there.
So is it mostly limited by simulations or observations?
I mean, I'm a theorist, so I would say I'm always limited by simulations, and the observations are great. Yeah, that's what I would still abide to here. I know or at least I know the limitations on this side better than the limitations on the other side.
You are an unusual theorist, because most theorists, if the observations don't agree, they just say the observers are crap.
So yeah, I think it's already 12. So let's.
All right, thank you all.
Great talk, Lorenzo.
Thank you.
We'll talk some more tomorrow.
Nice to see you not on Zoom. I think I saw, I haven't really thought about let me look into it. I'll see whether I can see something.
I'm very interested in these because we are planning to propose a new mission that will be much broader in energy band and angular and spectral resolution and full sky coverage. So that these things are very rare, but we could potentially see more of these.
More of this, okay.
So there's some really.
Should I